Good afternoon, everyone. My name is Yuxi. I'm from Synchrotron Technology. This afternoon, I wanted to share some stories and the work that we've been going on for building data engines for autonomous driving systems. I will go through some key components of the infrastructure and the tool chains for the development of autonomous driving technologies. All right, so the wide adoption of autonomous driving systems or autonomous driving technology has met a few challenges in the past few years in several fronts. One of the front is you actually trying to apply this technology at mass, at scale. And then when this happens, several things would happen at the same time. For example, functional development of autonomous driving systems needs a large amount of data. Because we're shifting from the previous development paradigm of cascading way of developing this system into a more data-driven way. So you need to collect a lot of high-value data, and you need to clean, you need to do a lot of labeling, which in turn turns the cost very high. And at the same time, you wanted to ensure this is safety-critical systems. You wanted to ensure a certain level of reliability. And by doing this, you need to do a large-scale validation and verification. So this will, in turn, incur a lot of cost as well. The second front is on the cost of development of such system. Nowadays, we're facing a lot of requirements on the versatile demands. For example, people want to make their cars work in different manner for different customer segments. And then this actually drives up the entire complexity of this system. And then at the same time, due to fierce competitions, especially in Chinese market, the R&D life cycle of such system is actually squeezed. So previously, it might take like 2 or 3 years to develop a certain type of cars. Nowadays, it has been squeezed to like 6 months or 8 months at most. And then at the same time, as mentioned before, data collection comes with high cost. You need to do a lot of hardware equipment, instrumentation. You need to do a lot of data cleaning and labeling and annotations. The third front is in terms of laws and regulations, how to regulate, whether we need to regulate high-level advanced, the deployment of high-level, advanced level autonomous driving systems, and how to certify. And also, there is issues around data compliance and privacy. So the development paradigm for autonomous driving system has shifted in the past few years from a hardware-driven to software-driven, and furthermore to data-driven methodology. And in the area of data-driven methodologies, we're facing the scale of more than 100 million miles of driving. And the perception system has been developed to be around multimodal sensors, so not just the LiDAR by itself or millimeter wave radar. And the scenarios that the system has to be facing now becomes open world interactive scenarios, not like in the old ADAS days where the scenarios are simple and structured. It's either simple cutting scenario or simple following the front car scenario. So this has driven the requirement on the infrastructure and tool chains for developing such systems. And here I basically break up the data-driven development into 3 steps. And I'm also making the analogy of drilling and refinement of crude oil versus the data-driven development technologies for AD. So for example, we need to start with the data logging. So we need to collect a lot of data from either operational vehicles, production vehicles, or from testing fleet. So we need to collect a lot of sensor data in the large volume. And this raw data is basically like crude oil. You need to mine, you need to refresh, you need to clean them to find high-valued scenarios, especially those scenarios where the system has been under pressure, for example, cannot perform very well. And those are the scenarios that you want to focus on in the next iteration. And the next step, you need to have a data platform on the cloud, which can process these raw data at scale. So for example, the data filtering, data tagging, and data labeling and annotations, these are all happen on the data platform on the cloud. And also for verification and validation purposes, some of these scenarios will need to be reconstructed in simulation environment. so that you can verify your next iteration of the software version, or you can do a regression testing to see whether you have made any progress or improvement on your system. So here you can see there are actually two types of loops here. One is the first loop based on real data. So you collect the real data from the real world operation testing fleet, and then you do some labeling on the data platform. Then you can use the labeled data to train your perception systems, to train your planning and control systems. You can also do a data replay by replaying this real data against your software stack on the cloud to see whether you see any regression or any improvement in your software development. So this real data incurs a lot of cost, and it's a slow process. So you have to collect the data, you run your fleet, you collect the data, you label them, then you can do retraining or validation of your system. The second loop is around synthetic data. So by synthetic means some of these scenarios are actually virtual scenarios run in your simulation system. And then your system spits out a lot of synthetic data, especially, for example, labeled data, depth labeled, or like bounding boxes, or driving lanes. These data usually comes with high volume, so you can generate a lot of them very quickly on the cloud once you have a pretty good seed scenario. So by seed scenario, I mean those scenarios that you have reconstructed from the data platform, especially like high value scenarios, the scenarios where the testing driver has intervened, or there's a large acceleration on the car, or there's difficulties in handling those scenarios by your system. So these high value target scenarios are the ones that you wanted to reconstruct or test against in the cloud. So the second loop is highly efficient. It can produce a lot of data in a relatively short time, and then it can be used to train and validate your system as well. So this is really a two-loop, two spinning wheel situations for this entire data engine. So next up, I will go through some of the details for each of these systems. First one is the data logging system. So nowadays, a lot of the testing fleet, testing cars, they're equipped with different kinds of sensors. For example, in this plot, I'm showing like 7 cameras around the car and 3 lidars, one main lidar on top of the vehicle with 2 lidars on the side of the vehicle to cover a more field of view. And then the data rate for this system will be very high, especially, for example, you have megapixel level cameras, you have 7 or 10 of them. And then these point clouds will come through Ethernet. So the data collection system or the data collection the PC will have to handle a large data rate comes in, and then at the same time to issue very accurate time signals. So for example, you need to trigger your cameras by aligning the camera exposure time with the LiDAR. The LiDAR is scanning like in a rotating pattern, and then once it reaches any view of either one of these cameras, you want the camera to expose to take a shot at the same time. So very high accurate timing signal will need to be provided by such system. And then in terms of data bandwidth, for example, it needs to be handled up to 16 channels of video input up to 8 to 10 megapixels each. And then LiDAR point clouds will come in through Ethernet. And then you also need to collect a lot of in-vehicle data. The control signals, they always come from these CAN or CAN-FD signals. So these control signals or the status of the car needs to come into the data collection PC as well. And then at the same time, you want to do some online labeling or online annotation. These are usually done by pressing some buttons or by recording some messages by the driver. For example, now I'm passing through a highway or I'm passing through a intersection. So these metadata are critical in terms of filtering or processing the data offline. So once the data is collected, it lands in one of these data platforms on the cloud. So several things would happen on this data platform. One is you need to do a lot of filtering and selections of the data. So a lot of times these data are meaningless. They're useless. They're normal operation situations where the system hasn't run into any trouble, or the traffic scenarios are very simple. So it's not useful to process them or to record them for further use. So you need to trigger or select your data based on few rules or based on the data collected by these sensors. For example, you wanted to collect data when the driver has intervened. The vehicle cannot perform as suggested, or there's a large acceleration or deacceleration of the car, or there's passing a very complicated intersections where the test driver pushed some button to record that this is a hard event. So based on these flags, you can do a lot of filtering in the selection to find out the meaningful, high-valued scenarios. So by scenario, I mean usually like typically a clip, like 1 minute long or a few miles mileage in terms of mileage size clips. And then what you want to do on the cloud is you wanted to label these data for further processing, for perception training or for validation purposes. The labeling usually is done in several manners. One is to reconstruct the local high definition map. So for example, by doing LiDAR slam or vision slam, you can reconstruct traffic lanes, the road lanes, you can reconstruct the dynamic traffic participants, and especially their types and their trajectories. So you need to reconstruct both static scenarios in terms of the high definition maps and some traffic infrastructures like traffic signs, lamps, posts, etc. And then you need to reconstruct the dynamics, the trajectories of those traffic participants, so that you have a full comprehensive information of what happened within the scenario. And then this data can be used in a lot of ways. You can directly train your next version of perception model based on this data. Or you can do a log-sim kind of regression testing in the simulation environment by just simply replaying this log against your next version of planning and control algorithms, for example, to see whether there is an improvement. So going into the details, for local mapping, usually it's based on, since this is testing car, usually comes with high definition LiDAR. So you can do LiDAR slam. And for production cars, usually you don't have that many LiDARs, or you even don't have LiDARs. So it must be based on some vision slams. So this will give you the local map of the scenario, and also like where the road markers or the line segments are. And then also it can give you a whole background point cloud for the local map. And then you wanted to do trajectory reconstruction. So this requires a fusion between LiDAR and vision. So you need to do 3D bounding box type of object recognition, and you need to do tracking. So you need to track each vehicle or each traffic participants in order to reconstruct their 3D trajectories. So these trajectories can be used to be converted into some scenario definition format, for example, Open Scenario 1.0. And this will give you the ability to run your scenario in the simulation environment. But just keep in mind that all of these reconstructions are in terms of object level. So this won't give you any 3D assets. This won't give you any rendering results. So all you have is simple wireframes of your map and the trajectories. So this is sufficient if you only wanted to do testings for planning control, for example. But if you wanted to do perception level algorithms, if you wanted to test or train your perception level algorithms, you need to do a vision level, 3D perception level reconstruction of the scenario. So there are several ways. One of the ways is just by looking at the wireframes of the map of the trajectories, you can match your predefined 3D assets onto the scene. So you can lay out the road surface, the road markers, the traffic lights, or you can match the informations to your assets of cars or vehicles. But another way of doing that is by simply utilizing the current methods on neural radiance fields or 3D Gaussian splatting field methods just directly reconstruct the 3D environment by utilizing multi-view camera images. So based on post-image multi-view images, these methods can give you pretty exact reconstructions of the environment. So this I'm showing two simple methods of hybrid rendering of nerve-based background, for example. And then in the foreground, we use simply 3D assets built in, for example, in Unreal environment. These can be mixed and matched. Or we can use nerve to reconstruct objects, obstacles, vehicles, and then we can put these kind of assets into a game environment, which serves as the background. So different ways of mix and matching and hybrid rendering in the game engine environment. So that was all about the data platform. So the next system is simulation. So simulation system usually provides you abundant label data almost for free. You don't have to do labeling because it's simulation. It knows every details of the ground truth. At the same time, simulation system can be used to do virtual validation and verifications to see whether, by reconstructing scenario simulation to see whether you have regressions on your development system. So there are several methodologies of building simulation system. The first one, or the most used one, methodology is based on game engine. So for example, Carla, AirSim, or there's several, LGSVR, for example, they're all based on Unreal game engine or Unity. So in order to build a game engine-based simulation system, you need to have a lot of assets. So these are predefined assets built by 3D artists. For example, we have all the traffic signs of Chinese traffic regulation, Chinese traffic environment. You have all different kinds of cars and vehicles. So once you have these assets, you have the map, you have the behavior description or dynamic behavior descriptions of the scenario, you can assemble them in a simulation system to become a 3D environment that your system can interact with. Next up, since we need to generate a lot of sensor data for the autonomous driving system, not just the vision images. So we need to have different kinds of sensor models. First one is simply the camera model, so to be used to generate images. The camera model usually is based on some physics modeling of both the length and the CMOS sensors. So in this kind of physics-based methods, you can simulate a lot of different phenomena, like dirty and dust on the camera lens, electronic noises on the CMOS, and you can simulate different kinds of weather, and also some lens aberration effects, for example, by using fisheye camera. So we not only need images, we also need point clouds because we wanted to simulate LiDAR. And there are different kinds of mechanisms used by LiDAR, for example, rotating LiDAR or some semiconductor-based vibrating LiDAR. So you need to incorporate different kinds of LiDAR emission patterns. So some LiDAR emits like in a single row while rotating, some LiDAR emits within a different pattern. So all of these patterns needs to be able to be reconfigured on the simulation. At the same time, different LiDAR uses different wavelength of the light, the laser light. So you need to consider different reflection coefficients on different kinds of materials for each of these wavelengths of laser. So those are all based on physics. So directly modeling how the sensor works. On top of the physics-based model, since after the physics modeling, you might still have some gaps, domain gaps, between the generated sensor signal versus the real signal. For example, on the leftmost image, this is an image generated from Carla, and the middle image is one of the images from the Kitty dataset. And you can see that despite of different contents of the scenario, the appearance of the image looks very different. especially like the color profile, the exposures, they're all different. So you wanted to be able to reduce this sim to real domain gap, because you wanted to be able to train your system in virtual environment while translating that capability into real data. So to tackle this domain gap, people usually wants to utilize some AI-driven or data-driven methods. One of the examples here is AI style transfer. This is basically by fixing the content of the simulation environment, we only transfer the appearance or the texture, appearance of textures of the image into a target data set. So by transferring the appearance of Kitty data set onto Carla, we can get something like the one on the rightmost. The appearance looks like Kitty, but the content comes actually from the Carla environment. So you have actual control of your content of your simulation, and the appearance becomes what exactly looks like in your target data set. So that was all about sensor models, but we have more models, simulation models that needs to be used in a game engine-based environment. One of the models is traffic behaviors. So for the testing and validation of L3 systems and above, L3 autonomous driving systems and above, people realize that we need to have interactive environments, not just the simple ADAS environment where everybody follows the fixed trajectory. There's no interaction at all. So in this traffic environment, we need to have smart agents, smart traffic participants that can interact with the ego vehicle in a smart manner, in a naturalistic manner especially. So we need to train some policies, AI-driven policies that control each of these vehicles so that they can interact with the ego vehicle in order to make this entire scenario valid. So not only can we do naturalistic modeling of the behavior, we can also do adversarial modeling of the behavior. So we wanted to increase the testing efficiency. We wanted to expose more deficiencies of the system with less mileage, with less number of scenarios tested. So we can optimize the driving policies of these NPCs so that their behavior becomes more aggressive towards the ego vehicle. They can conduct any very challenging behaviors against the ego vehicle to exert more pressure. So actually by utilizing this adversarial behavior model, we can expose a lot of problems especially on the planning and control module of the ego vehicle. Other than the simulation models, we need to have some tools and in order to make simulation testing more easy for us. For example, we need to have scenario editor. This is a graphical user interface that lets us edit the behavior or trajectory of each traffic participants and how they interact with the ego vehicle. We need to have sensor configurations, like basically visualize the FOV field of view of each sensors and how they installed onto the ego vehicle. So this is all built around Carla to make it more easy to conduct simulation environments. And of course, all these kind of assets needs to be man-made. But nowadays, there's a lot of new tools coming onto the market that would make this asset building more efficient. For example, NVIDIA has a lot of procedural-based modeling tools that you can use. For example, Houdini, these kind of tools that will help you quickly set up a large environment, large 3D scenes in a relatively short time frame. So these are all game engine-based methods for building simulation system. And then there are some new methodologies coming up trying to avoid the cost or make it faster to build a simulation system. One of the ways is to do 3D reconstruction directly from data. This is one of the methods mentioned. This is in GOSIM. So basically, by looking at continuous frames or videos from different angles, you can reconstruct this 3D environment quickly by using these neural radiance fields or neural feature descriptors. And then once you have a reconstructed 3D environment, this has no domain gap. Everything is reconstructed from real data. So this has no domain gap. But you need to be able to do some editings on the scenario. So not only can you reconstruct the entire scenario, you can edit you can put in new assets. You can change the trajectories of some of these traffic participants. And seen in this two plot. So the first one up is once you reconstructed 3D information, you can change your viewing angle. So we can do a multi-angle reconstruction. The second one is you can actually take one of these front trajectories, like one of these cars, and then modify its trajectory so that it can follow new trajectories. And you can actually see some differences between the background and the front vehicle. There are some artifacts there. This is all due to the reconstructions. So you cannot reconstruct light or textures. It's very hard to reconstruct lighting condition and textures. So you can still see some artifacts by manipulating the background. Another way of doing simulation is by running one of these world models. So basically, world model is an internal representation of any AI agents about the environment the agent is interacting with. So the agent can do a lot of imaginations in the world model. It can do different kinds of trajectory mapping. It can interact with the world model. And the interaction efficiency is very high compared to interacting with the real environment. So this is Drive Dreamer. Basically, by utilizing these diffusion models, and then they can do a lot of conditioning. For example, by using a reference image and some HD maps and the layout of 3D bounding boxes, just given these initial conditions, it can generate continuous frames. So this is basically video generation based on some conditions. And then in between, they use a lot of transformers and diffusion models to make sure these conditions can be taken into account during the diffusion denoising process. And then at the end, you actually get some real data out of it. So these are some displays of imagined scenario. See, these are all generated by the AI model. Nothing is reconstructed. Nothing is built by 3D assets. Just by giving the model some layouts, for example, how the road goes, the road network, and the 3D bounding boxes of different objects, then push everything through this diffusion-based backbone, then you will have some realistic images, continuous time and temporal and spatial continuous images or frames coming out of the ego vehicle. So world model nowadays has been, there's a trend to using world model within a autonomous agent system. For example, in autonomous driving system, if the system has a world model inside of it, it will be able to imagine or unroll different kinds of behaviors and to see where that goes. For example, it will be very efficient to evaluate any planning actions, whether that's safe or not, whether that's more efficient or not. And at the same time, the same world model can be taken out of the AI agent to be used as a neural simulator. So the agent will execute some certain kind of actions, and the action taken by the world model will generate the new sensor data seen by executing these kind of actions. And then the new data will come into the agent to do the next round. So this basically closed the loop by utilizing the world model. This is a very efficient way of interacting with the simulation environment versus interacting with a game engine-based environment. For example, it will take a lot of effort to build the world first. And also at the same time, the game engine environment is not open world, so it's constrained by what you actually build before the testing. And also much more efficient than deploying or testing the embodied AI agent with real world. So in real world, you're constrained by a lot of artifacts, constrained by a lot of maps or safety concerns. So by interacting with the world model actually allows the embodied AI agent to be evaluated more efficiently. But there are some drawbacks. There's a pros and cons for employing world model. The pros are, learning real model. The world model can be learned from real world data and can be learned from real world dynamics. So everything is real. There's a very much less domain gap there compared to game engine-based ones. It's capable of handling uncertainties, occlusions, or noise in the data. So if something is occluded in your data, the word model can infer that part of the data in the next several frames. The last one is, of course, the word model can be incorporated into AD systems to provide recognition and predictive capabilities. So these are the promising effects that within a word model. That's why a lot of people are talking about they need to incorporate word models into a simulation system. Of course, the drawbacks are it's not yet physics accurate yet. A lot of people saying Sora, video generation models like Sora might have been able to infer some physics laws within it. But since this is all probabilistic, data-driven ways, you cannot actually learn physics laws within it. But given the more amount of data, given more complex systems, one day it might be able to infer some physics laws within it. And there's insufficient 3D consistencies. If you enlarge one of those plots that the videos that I showed before, you can see some inconsistent 3D effects in it. And then it's kind of difficult to be conditioned on actions. Drive driver can be conditioned on some steering wheel, steering angles, and acceleration. But generally, conditioning on actions is very hard. So this is a very necessary component if we want to have a world model serve as a simulator. So last, a bit of summary. In order to develop autonomous driving systems in a data-driven way, we need to have a scalable data engine. The data engine needs to be composed, to be combined with a high definition, high bandwidth, time-accurate data logging system to collect all these operational data or testing from testing fleet. Also, you need to have a scalable data platform on the cloud for all kinds of data filtering, labeling, and scenario reconstruction workloads. At the same time, at the end, you need to have a so these are all the real data path. But in order to utilize synthetic data, you also need to have a performant and versatile simulation systems. So these simulation systems can be built from game engines, which gives you physics accuracy, but it comes with relatively high cost. So you need to build those 3D assets first. You need to set up the entire, so game engines are actually heavy. You can also build it from some reconstruction technologies. So all the environment will come from reconstructed data from your testing fleet. So this gives you photorealistic environments. You can do some constrained, limited viewing angle shifting, but it cannot support any view. For example, you cannot see the back of the car. So, and at this time, it's very difficult to do inverse rendering. So it's kind of hard to alter weather and lighting for these nerve-based methods because all the light effects are baked in to the texture. It's very hard to decompose the texture from some of these effects come from lighting, some of these effects comes from the texture itself. And the third method is based on word model, also gives you photorealistic. It's very data efficient, so it can directly learn from data as long as you give it a large amount of enough data. But at this point, it's not physics accurate yet. So people usually can use it to train your perception system, but it's very hard to do testing or validation by using this word model because it's not yet physics accurate. It's not yet 3D consistent, spatial temporal consistent, and it's hard to control. So you cannot, based on your output actions from your ego vehicle, it's kind of hard to alter the viewing angles or the behaviors of the objects within the scene. So yeah, this is all I have to say about data engines, and thanks for listening.